Hello everyone, welcome to our paper presentation. The title of the paper is Parframe MAP Prediction for Continuous Performance Monitoring of Object Detection During Deployment. My name is Quazi Marufur Rahman and my co-authors are Niko and Feras Dayoub. We are from Queensland University of Technology, Australia. First, I will talk about the problem we are trying to address and why this problem is important. Later, I will present the approach towards addressing this problem along with the related experimental result. Object detection is a crucial part of many autonomous vehicles to ensure the safety and reliability. It is mainly used to detect critical objects like other vehicles and pedestrians on the road. Because of its importance, there is ongoing research to improve the accuracy of object detection systems. However, we cannot guarantee a consistent deployment performance due to the difference between training and testing data and many unavoidable factors like sensor failure or degraded image quality. As a result, object detection performance fluctuates without any warning while on board an autonomous vehicle. To solve this problem, we can develop exceptionally accurate object detection system. However, due to practical reasons, we cannot collect image dataset for all future scenarios to train a perfect object detector. Although we can have summary metrics of the object detector using a holdout dataset in the deployment phase, the accuracy might drop below that threshold. Another possible solution is to identify this performance drop. So, without the need to increase the detection accuracy directly, a performance drop identifier can protect the autonomous vehicles by providing crucial alerts during periods of silent failure. Therefore, we are proposing object detection with self-assessment capability to detect instances of performance drop during the deployment phase. This figure provides a visualization of the problem that we are trying to address. We used a vehicle and pedestrian object detector on a continuous stream of images and measured the mean average precision of 10 continuous frames at a time. Let's assume this is the test dataset. The top figure is showing the performance fluctuation during the deployment. The green line indicates the mean average precision in the evaluation dataset. We can see the frequent drop in performance than the expected threshold. The bottom figure is showing some false positive and false negative errors made by the detection during this deployment phase. Let's talk about the previous Let's talk about the previous works. We can roughly divide the previous works that focused on some kind of performance monitoring into two groups. We can define the first group as the failure prediction. They predict the performance of a model only looking at its input. The next group can be defined as failure detection. This group evaluates the output of a model to find out the expected performance. We have enlisted some literature from both of these groups in this slide. Here is a basic block diagram of our approach that we use to address the object detection performance monitoring problem. Let's assume we have trained an object detector to detect pedestrians and vehicles. We will refer to this as the basis. We have a holdout dataset and we use the basis to detect our target object from this dataset. Using the ground truth and detection, we compute the mean average precision per frame and extract features from the basis internal layer. We select a threshold lambda, which is the k percentile of all MAP of the holdout dataset. Using this threshold, each frame of the holdout dataset is labeled as success or failure. Using the collected features and binary target, we train a binary classifier to predict success or failure level for each input image. We refer to this model as the alert. This figure shows the architecture overview of our proposed performance monitoring system. We extract features from the last convolution layer of basis to train the alert system. During the deployment, alert takes features after each basis inference and predicts basis performance for each individual input. Here are the overall settings for all of our experiments. First of all, we have used Kitty and BDA 100K object detection dataset for all of our experiment. Besides, we have used faster RCNN using ResNet 18 and ResNet 50 as backbone to detect pedestrian and vehicle objects. Two different settings have also been used in similar dataset settings. In similar dataset settings, we trained and tested the alert system using different splits of the same dataset. In cross-dataset settings, we use different splits of different dataset to train the basis and test the alert system. Moreover, we have used area under the receiver operating characteristic, area under precision recall curve, true warning rate, risk averse metric, and MEP versus declaration rate to evaluate our proposed approach. Last two metrics have been adopted from the work of Zhang and the colleagues. This table is showing the AUPRC and AUROC scores in the similar dataset settings. In the first row, KT/KT/18 means we have trained the basis using a training split of KT dataset and tested alert performance on predicting basis performance drop on KT test dataset. Faster RCNN using ResNet 18 has been used to train the basis and the collect features for the alert system. We extracted multiple features from the last convolution layer of basis, and the table shows the concatenation of mean, max, and standard deviation features work better than all other features. This table shows the AUPRC and AUROC score in the cross dataset settings. In both similar and cross dataset settings, the mean, max, and STD features outperforms all other extracted features for detecting the performance drop of the basis using the alert system. Using the best performing feature mean max STD, we use the true warning rate metric to determine the quality of the alert system in raising a warning against basis performance drop. Here, the warning rate is the ratio of correctly raised warning versus the total number of frames with per frame MAP below the critical threshold. The results in this table shows that in cross dataset settings, the true warning rate is higher than the similar dataset settings. In risk averse metric, we evaluate alert's capability to trade off the risk of making an incorrect decision without making a decision at all. This metric gives basis +1 and minus 0.5 respectively for correct and incorrect prediction. Basis will get 0 point if it does not make any decision considering the warning raised by the alert. For crucial systems like self-driving cars object detection, we expect basis to trade off incorrect decision for no decision. Figure A shows the point per image earned by basis when it operates with and without considering the warning raised by the alert in similar dataset settings. In all cases, basis earns more points per image if it abstains from making an incorrect decision, taking alert's warning in consideration. Figure B shows the risk averse metric for cross dataset settings. Now we will evaluate the basis accuracy score for different declaration rates. Here, declaration rate is the proportion of images on which basis operates. The rest of the images are discarded assuming that basis performance MAP will be lower than the critical threshold on those images. To calculate this metric, we first sort the images in the ascending order of the alert confidence. Next, MAP of the top declaration rate percentage of images are computed to plot the MAP versus declaration metric. For a perfect alert, the MAP for low declaration rate images would be very high and decreases gradually as the declaration rate approaches 1. In figure A, we show that MAP score for 4 different declaration rate in similar dataset settings. Here, the MAP score drops gradually with the increasing declaration rate. Figure B shows this metric for cross dataset settings. Here's a summary of this talk. We are proposing an introspective approach to performance monitoring of object detection during deployment without accessing to any ground truth. We are proposing an internal integrated feature based on the mean, max, and statistics pooling technique for performance monitoring. Besides, we are introducing the use of per frame MAP prediction for continuous performance monitoring of object detection. Thank you.